And we are live. Hello, everyone. This is Virtual Jug. My name is RxJava, and we are very happy that we have this session today. It's a beautiful Wednesday. It's almost summer. Actually, it's April. And today we are extremely happy to host another Oleh Dokuka, and the session will be about the reactive performance. Oleh, how are you doing?
Hey, Oleh. Glad to meet you again, and I'm fine. What about you?
I am absolutely perfect. This is a topic that is of a great interest for me personally. I know that you might be mentioning Graal compiler there, and as a developer advocate for GraalVM project, I'm extremely excited to hear whatever you're gonna say. I hope you're gonna say good things about it. So, for our viewers, before we start, I hope everything is going fine. I can see the video on YouTube running. Let me just share the screen and just give you 2 bits of information, like literally show 2 slides for you. Hope you can see my screen. So today's session, you're watching Virtual Jug, the virtual Java user group. Today's session is reactive performance. Oleh's Twitter is Oleh Dokuka. You should follow him. If you don't get the chance to ask your questions today, you should ping him. If you are watching this live, you can ask questions in the Slack group. So join our Slack, and there is a live session channel, and you can ask all the questions there, and I will find the opportune moment during the presentation and ask Oleh your questions, right? And you are welcome to share the virtual jug and this particular session. And if you have any feedback about the quality, about the topics, about the presenters, and how extremely excellent they are, you can tweet at the virtual jug or at me personally at Shalev. If you're watching this on YouTube and you don't feel like the quality of the video is up to your expectations, please use the cog icon on the video widget to increase the quality. Typically, it goes up to 720p, so it should be absolutely fine for watching anything, literally. Right. So with all that important official organizational info out of our way, I'm very happy to present Oleh to you. He is a contributor to Project Reactor. He's an open source committer. He is a consultant and a Java software engineer for, I think, many years. Well, reasonably many years. He looks really young, but a sufficient amount of years to become an expert. And he wrote a book, right?
Yeah,
about the Project Reactor. I aspire to write a book one day, so when I grow up, I want to be more like you, Oleh. So without further ado, please welcome Oleh, and I will see you in the live session channel on Slack. Oleh, it's
all right.
The floor is yours.
Yeah, let me share my screen first and disable my camera in order to improve the performance. So yeah, do you see it? I guess you can see yourself. All right.
Yeah.
So yeah, I guess we can start. And today's topic is reactive performance. This is the first part of this reactive performance presentation, because I'm planning to give another part. And in order to save your time and in order to make this watching and this video as much as possible productive for you, I would like to start with some slides that describes what is this talk about and for whom this talk is especially. First of all, I expect that everyone who listens this presentation and this talk have ever heard about reactive programming, reactive streams, about RxJava and Reactor 3, for example. I expect that you know something about that, you tried that, and you want to tune your performance of your reactive application where you are using one of those libraries. And I would like to pay attention that during this talk, we are going to look at the reactive streams under the hood. We are going to understand what is going on inside reactive streams, how it works, and so forth and so on. Then we will try to understand what is hidden in RxJava 2 and Reactor 3, what hidden properties they have, and how we can tune them. Then we will try to find out maybe better GC for reactive streams and try to optimize our streams with Graal as Git compiler. So during this talk, you should expect those topics, and you should understand that you have to have some knowledge about reactive streams and understanding of essentials of reactive streams like back pressure control and asynchronous message passing and so forth and so on. And you should take into account that without those knowledges, you will probably won't get fully this conversation, this discussion, and won't get the whole knowledge about the reactive tuning without understanding the essentials. So let me start. And if you still think that this topic is for you, let me introduce myself. As Oleg mentioned, my name is Oleg. I'm from Ukraine, from Kyiv. I work for Netify, where we are building reactive streams over the network. So we are building new future protocol called RSocket. And also I'm contributor to Project Reactor, and I'm doing my best to improve that project from popularity side and as well as from performance side. Also, I'm organizing and helping with organizing few of the biggest conference in Ukraine, like GEConf and DevOps Ukraine, and improves my local community by organizing Java user groups. So, first of all, you should ask the main question: should we care about performance in reactive streams? In order to answer this question, I'm going to show you a few screenshots. The first one is this. This is a performance comparison between Java streams and reactive streams. And as you can see, there is slight performance difference, like 5% in performance. So yeah, not that much, but you can just imagine that in real production, where we are running a lot of servers, where we are handling thousands or millions of user requests, 5% of performance can worth something, especially can worth some customers' money or something like that. On the other hand, we can take a look at another performance comparison between reactive libraries and between plain for loop. And as you can see, if you can pay your attention to those numbers, you will see that performance difference between plain for loop, between plain imperative programming and reactive libraries is not that 5%, but 5 times higher or 5 times faster than reactive streams. So now you should ask your question, why should we care? And I guess seeing those numbers, you should understand that we should care about performance, because performance overhead of reactive libraries is huge, like 5 times overhead. So let me quickly start with the agenda and explain what we are going to do today. First of all, we are going to understand why we have this overhead in reactive libraries. Then we are going then I'm going to share some tuning types and tricks. This is not code changing. As I mentioned earlier, this is the first part of reactive performance presentation. And in this presentation, we are going to talk about no-code changes, tuning types and tricks. Because you're running your application in production, you're already wrote your code, or you're planning to write something. And if you are the first part of the audience who has already written some application using reactive streams, you probably won't be able to rewrite your code or refactor it just after this presentation. Thus, I'm going to share some minimal types and tricks in order to improve your performance without any code changes, just by tuning GVM and so forth and so on. And finally, we are going to experiment with a real app written fully in reactive streams using RSocket and Spring. And we are going to understand whether we can improve the performance of this application using previously mentioned types and tricks. So let me start, and let me quickly introduce and explain what overhead we have in reactive streams. First of all, we have to start with streams lifecycle, because this is the most essential part of reactive streams composition, reactive streams assembling, running, and so forth and so on. And starting from that point, we are going to understand what overhead we get with reactive streams. So first of all, there is a three main lifecycle stage in reactive streams. The first one is when we call from array, when we call map, filter, and whatever operators. And this stage is basically calling assembling, because we just assemble our pipeline. We don't run any data. We haven't had any subscription so far. We just combine and we just build our pipeline through we are going to send our data. So this is just an assembling stage where we don't have anything so far, just a pipeline of objects. The second stage in the lifecycle of reactive streams is basically when we subscribe to this stream, and this is basically a terminal operator when we asking for some data and exposing our intent to receive those data. So at this stage, we are passing to our publisher or reactive stream the subscriber object, which is flow up to our publisher, and using this subscriber publisher start executing some and calling some methods like unsubscribe, through which publisher sends its subscription to the subscriber. This stage is basically called a subscription time, because we don't have any data so far. At this stage, we just exchanging our, we are doing handshake or something like that, and we just exchanging subscriber versus subscription in order to start our communication. And the final stage at reactive streams lifecycle is actually runtime, at which we are start calling or requesting data. For example, we are going to request 5 elements from our publisher, and our publisher starts sending the data to our subscriber, and we somehow are going to process them. So this stage is basically called runtime, at which we are actually handling some data, processing them, and somehow react to all incoming events. So this is basically what is going on when we start doing actual communication between, for example, client and server in new web flux and so forth and so on. So let me quickly show you this basic lifecycle by debugging some small plain application, as which I mentioned it on my slides. So hope everyone will see my code and my IDE well. And what I have here, basically I'm using in my Project Reactor, which is from Pivotal, which is extensively used in Spring Framework 5. And here I have really plain and uncomplicated code, which I'm going to run right now. And I'm going to explain what is going on under the hood in order to ensure you that everything works as I mentioned. So first of all, we started assembling the code. We got our publisher created, and now we are going to subscribe to this publisher. At this stage, we are going to create some Lambda-based subscriber. So this is built-in feature of Project Reactor. You can create your subscriber just by calling new subscriber and passing in the same way. But I'm going to just create no ops subscriber, as you can see here. And in a few more steps, I have to skip this stuff. I'm going to pass, and this guy, come on. I'm going to subscribe to my stream using normal method. At that stage, I'm just passing through all some additional stages my subscriber, some internal invocations, And after all, yeah, we got to Flux array, which is implementation of array of wrapper around array, like publisher for array. And now at this stage, I'm going to enter the Flux array subscribe method, which is the most interested for us, the most interesting for us at the moment. At this stage, I'm just going to walk through some conditions. And as you can see, here we got a subscriber. So this is basically the subscriber I mentioned on my slides. And now, as I said, we are going to send a subscription to our subscriber. So at that stage, we are going to just doing subscription or data exchanging. And by doing that, yeah, I have to that guy. I have to bypass that guy. And here we go. We got our subscription. And after all, we can ask for some data. For example, in that case, we're going to ask for all data by sending long max value request. So at this stage, we just finally exchanged all required, or we did a handshake between our publisher and subscriber. And now we can start requesting, or we can start doing runtime at this moment. For example, once we ask it for some data, publisher reacts to that request and will start sending elements that it has in his arsenal by calling on next method. And then we are going to consume every element that publisher sends to us, and so forth and so on, and so forth and so on until stream completion, which means that we don't have the publisher send everything that it has, and it doesn't, and it sends only the final terminal signal to its subscriber. So this is basically it. And now I hope you ensured that we have all these mentioned stages in our reactive streams. So basically, assembling, subscription, which means sending a subscriber to publisher and receiving subscription, and then runtime, which means sending all this data to the subscriber. All right. So this is the first stage this is the first part that you have to remember about reactive streams, but this is not the most important, because in general, let me summarize quickly. Assembling means creation the publisher, subscription means exchanging data, and the rest is runtime. So if you remember what is going on inside Java streams, you should remember that Java streams has something similar to reactive streams. If you're going back to our IDE and take a look at what is going on with, for example, is real Java streams, for example, like this. Yeah, let me quickly create some example for you. And calling for each, we will basically got almost similar execution flow as in reactive streams, because yeah, system out ln. Because under the hood, we create the same stream object, which is producer, and by calling for each, we are notified the streams that this is a terminal operator, and we wanna start consuming some data, which almost works like in reactive streams. So counting that fact that reactive streams is almost similar to Java streams, we can create some basic comparison of object overheads that we have seen that we might see during during the demo. So to summarize, reactive streams creates one object, one publisher at assembly time. Then it creates two objects, one subscriber and one subscription at subscription time, because this is this contract is done for supporting back pressure and resilience in streaming. So we use subscription in order to expose how many elements we are ready to consume, and that's why we have to have all two objects in this at this stage. And finally, at runtime, we can produce basically n elements, NT elements within the stream, but this is actually the logical elements or events that we want to handle and process in our stream. In Java stream, we have something similar. So at assembly time, we create a stream, which is basically a wrapper around array in our demo that we have done just a couple of minutes ago. And at subscription time, we provide an implementation of terminal operator. But in contrast to reactive streams, here we produce only one object, because Java streams is just push-only model, so we don't have to create subscription here, and we can just produce one terminal or subscriber or operator that notify publisher or stream to start sending data. And at runtime phase, we have almost similar behavior. We just send in data through our pipeline and produce n elements through our stream. However, the main difference between Java streams and reactive streams, and the main in order to show the main overhead of all the streaming, is by comparing imperative streams or plain imperative programming, the plain for loops that we can write in order to iterate over the array. And at that stage, we don't have any assembling, we don't have any subscription, we just processing data, and that's it. And the overhead is minimal, and the overhead is just element that we producing and processing during the iteration. So counting that fact, we can do some basic math in order to understand what overhead we can have in terms of produced number of objects. So for reactive streams, we usually create n elements, so n logical elements that go through the pipeline. We create m operators, which means we create m subscribers, m subscriptions, and in some cases we create some additional. So I mean, like, we produce m object operators, which is m publisher for each. For each operator, we create new publisher, and for each at each subscription stage, we provide a wrapper around subscriber, and in some cases we provide an additional subscriptions. So let me show you how it works under the hood in order to explain what is why we have that much objects during the building reactive pipeline. So if we're going to look at this plain stream, let me put this here, and let's just write a few mappers with function identity, and for example, few naive filters like that. From the first glance, it seems that we shouldn't have any overhead so far. But if we take a look at what is going on under the hood, we will see that each publisher, each current publisher, on every map call, on every filter call, on every operator call, wraps using another operator. So basically what is going on, we are producing the objects chain, which delegates all the invocation of all methods. The same we have for chaining our subscriber. So we receive the subscriber, and we wrap this subscriber into another business logic, or into map subscriber. In this case, we have some optimization, of course, in reactive streams, and from time to time, plain operators includes and combines at the same time a consumer or subscriber logic and producer or subscription logic, and in that way we reduce the number of created and produced objects. But when we do some multi-threading data processing, like we are sending data through publish on or similar operators, in this cases we can create some additional subscribers and some additional subscriptions, which produce produce one more object to garbage collector. In contrast, Java Streams is a little bit simpler. So on average, we just create an element during runtime and produce one more wrapper for every operator, because Java Streams almost design it in the same way, or Reactive Streams design it in the same way as Java Streams. So their overhead are pretty similar. Finally, for imperative data processing, we just create only n elements and that's it. And we reduce the number of produced objects for, you can imagine how many operators you are using in your reactive application at production. And you can reduce, by using the plain imperative programming, you can reduce the number of created objects a little bit, of course. So after this intro to what is going on inside Reactive Streams, we have to ask yourself where this object overhead impacts performance, and why should we care about how many objects we produce in our application. So usually when we build plain Spring application, when we create a plain CRUD application, we usually write something like that. So we create a plain, for example, post mapping that accept one object asynchronously in that case. So we receive mono, for example, of some order, and after some processing, we return that mono. However, since we like general idea of reactive programming, which means some functional piping where we can separate all the stages of data processing on the separate maps, for example, we can write something like that. And you should wonder, why should we care? How can this code impact the performance? However, if you measure that plain application, you will get, for example, something like those benchmarks. So in that case, let me explain shortly what is going on here. Currently, I'm showing you a GMH Java micro benchmark of imperative code that doing the same business logic as you have seen on this slide. Not this slide, but this. Doing exactly the same execution of exactly the same methods like here, versus this code that you have seen just a moment ago, versus the stream of, in this case, of 2 elements, because I had to create a stream of 2 elements in order to show you performance impact. And if we do some basic math, if we compare the performance of those programs, we will see that overhead of reactive pipeline is about 15% versus plain imperative program with the same identical business logic. So now you should think whether I have to write that much reactive operators in my pipeline. However, sometimes, like, this is an example of just 2 element stream. However, in reality, we have a pipelines of long running streams. For example, from time to time, we can process 10 elements or even 100 elements. And for example, for 10 elements pipeline, we have only 6% overhead, which is better. And if we have really long running stream, for example, I did a performance measurement of the same pipeline of maps versus the same business logic written in imperative style, but in that case, the business logic the business logic was processing 1 million elements, and by measuring these applications, we will get only 3% of overhead, which means the more elements we have in our pipeline, the more long running our pipeline is, the less overhead we get during the processing of our during the business logic in our application, which means having only one plain CRUD application which handles which handles one post request using mono and respond using mono can impact your performance a lot, around 15%. And in case you're writing real streaming application, real fast long running pipes, which doesn't create on every request a new stream, in that case you will get around 3% overhead. All right. However, if we put all those measurements on the plot, we will see some dependency between the data. And of course, if we provide some or continue doing some measurements with reactive pipelines and imperative pipelines, for reactive pipelines, we will see that it's for the short number of elements, or for just a few numbers of elements in the stream, we will have a really huge overhead. But once we get more and more elements within one stream, we will approximately goes to some trend and to some basic overhead for streaming. For example, in that case, this overhead will be for 4 maps will be around 2 or 3%. And now you should wonder, what else causes those overhead? Because in case of 10 millions of elements within the stream, our stream will be really long-lived, and garbage collector won't do any additional work for creating and allocating and deallocating the publisher and subscriber and all related elements to reactive streams. So what else can cause this overhead for reactive pipelines? In order to understand that, we have to go deeper, and we have to understand what is going on within runtime phase. So basically, when we build a pipeline, we produce a few objects like from array, map, subscribe. And at this stage, when we start sending data, we will have something like this. We will have basically invocation of first map, and we will have some sending of circles. After this, in order to apply mapping, we will have to apply function provided to our publisher. So we actually apply business logic by mapping one element to another. And after all, we will call another subscriber, which is downstream subscriber, by calling on next method is square after some mapping. And after all, we will call another on next after mapping, and so forth and so on. So basically, what is happening is chaining of methods, because as you can remember from previous part, is that we have basically a chain of responsibility within our reactive streams. So basically, in order to, for example, request elements, we will have to call every subscription and request n elements through every wrapper until we get to final publisher, and publisher will call on next method on our subscriber with this element. And after all, what we will have another chain of invocation, which will be invocation of next method through all available or chained subscribers within our pipeline until we get again to request method, and we will get the same picture as before, and so forth and so on until we produced all the data. So basically, let me quickly show you what is going on here. So as I said, here we have some our basic pipeline, and if we let me go quickly to our Lambda subscriber and put a breakpoint here and run our stream. And yeah, here we go. We subscribe to our stream, and now we are going to the chain of our subscriptions. So this is the bottom of execution. This is just the first unsubscribe call. And after all, we are going to another subscription, which is flux filter. which just bypass this request method to upstream, and the same for map, and the same for another map, and the same for another map, and the same for another map, and another, until we get to our publisher or actual source of data, which starts sending data. And basically, this data sending just end up with plain on next invocation, which looks like that. So let me do that. Yeah, here we go. Here we got the first element, and here we start traversing through the business logic. Since here the mapper is just an identity function, so we don't have anything to do. We just execute that function and that's it. Then we are going to call another mapper through on next, and another mapper through on next, and another mapper, until we get to our filter. Here we in the filter, since our predicate is always true, invocation we just receive true, and we call another on next method, which will end up with our consumer, actual consumer. So this demo just basically shows what is going on inside under the hood at the runtime. And what is going on is just basically sending the element through the pipeline of objects of subscribers. We just delegate their invocation to another subscriber, to another subscriber, to another subscriber, until we get the final endpoint. And that's basically it during the whole data sending. Nothing complex, but as you can see, basically what we have here is just method invocation. So let's back to our slides, and let's just talk again about overhead. And in that case, methods call overhead. As you can know, one of the expensive operation in Java is, and in programming in general, is method invocation. And maybe you heard something about inlining, where at runtime, for example, in Java, Git compiler tries to inline some method invocation in order to reduce the overhead that we get by calling the methods. So in general, to summarize what overhead comes with the streaming paradigm, for reactive streams, we have in general m on next method invocation on our subscriber, because where m means the number or equals to the number of produced operators in our pipeline. In turn, we have n invocation of real function, which means invocation of real business logic, and we have m invocation of request method because m could be only one invocation at the very beginning, where we just says, okay, give me all you have by sending lone max value, or we can send request 1, 1, 1, 1, 1 on every element we received. So in that way, we can just we can just have plain pool model, but with reactive streams. So it depends in many cases. We are going to take a look at those cases a little bit later. But in general, we have some overhead in method invocation in reactive streams. Comparing to Java streams, Java streams has only two basic invocations, which means sync invocation or calling sync accept method for new element. It could be a little bit different. So it can depend on some operators within Java streams, but basically it's just one invocation just an invocation for every element on the consumer data consumer, with an invocation of real business logic or real function, which does some business logic for you. And finally, comparing to imperative programming, we just have an invocation of real functions. And as you can understand, in that case, where we have just plain method calling, the JIT can work well, where with Java streams and with reactive streams, inlining of all this calling within the sync and within the subscribers can be a little bit challenging. So to summarize, in general, for reactive streams, we have around 3x overhead in method invocation. In general, we have to produce far more instructions than for plain traversing over the in the for loop, for example. As you have seen, we have a lot of verification inside the next method for mapper, inside the next method for filter. And I'm not talking about more complex operator like flat map or publish on and so forth and so on. And in general, having this paradigm and having this chain of responsibility of invocation of business logic in our reactive pipeline, we have less chance to get a proper inlining at runtime by JIT compiler, just-in-time compiler, which means that here we can have this 3% overhead, for example, for only 4 mappers, or we can have even more runtime overhead or invocation overhead when we have far more operator in our pipeline when we are doing a real business logic processing. So to show you the possible overhead that you can have and that overhead that comes in this example is basically based on the invocation and basically on some invocations of reactive streams and basically on some additional operators. Of course, when we write a lot of operators, the runtime will be much more complex than in plain imperative programming. However, the plain runtime, like plain series of maps and filters, can't produce that huge overhead that we can see in this benchmark of Scrabbles. In order to understand where we can have a few more overhead in our data pipeline, we have to go in a little bit deeper and we have to talk about some operator structure and understand what is going on inside under the hood in some operators. So basically, the most common and expensive operators that we can use during the building of our application is the following. And I ordered all the next list of operators by their impact. So from my point of view, the most expensive operator and the operator that impacts your performance a lot during your data processing is flat map. I'm going to talk about flat map a little bit later, but for now, this is the most expensive operator you can use in your reactive pipeline. The next one is publish on, and publish on has a little bit less overhead, but basically this is overhead related to switching between the streams and some additional data structure used under the hood. Almost the same overhead you will have with publish operator in order to multicast data between few subscribers, and a little bit less overhead you will have with concatenate, which also has under the hood some additional data structure in order to handle in order to process data. So let's take a look what is going on under the hood for those operators, and let me quickly show what kind of overhead we have in reactive streams when it comes to using one of the mentioned operators like flux, flat map, like publish on, and just publish operator. So here we have a plain example of plain data processing where we have just a flat map which flatten a stream, a range of elements which runs on a different thread. Since reactive streams is designed for multi-threaded and designed for handling data in several threads, or making it possible to process data from several sources, which could run on several threads. One of the options that we would want to write is flatten the data, or flatten the request to another service, or requests to another services. And during this execution, in order to handle all this data, and in order to not shoot into your lag by improper synchronization and so forth and so on, Reactive Streams does everything for you, and Reactive Streams serialize all the execution. And in order to serialize your execution, they use queues, of course. And under the hood, if we take a look at what kind of queues I'm talking about, I'm going to show you some additional utility class called queues, which is heavily used inside Reactor. And I'm going to just put a breakpoint at this stage in order to show you how many queues we can produce during using the plain flat map operator in that case. So let me just start this application and show you how many queues we produce during the, not this one, but this one. Okay, here we go. Here we created the first queue, or asked for creation for the first queue, and that happened at the very beginning of pipeline assembling. So once we entered the flat map, we produced the first queue, which is required for some data prefetching, which is designed for a little bit better performance. Then we are going to, as you can see a little bit later, we will produce another queue, which is used for our internal streams in order to enqueue all the elements that we requested for those internal queue. And here we create we ask for another queue producer. And then at every stage of the invocation, we approximately produce a few, let me put a breakpoint here and here in order to show how many queues we produce during the runtime. So here we go. Here we ask for queue supplier. Here we ask for queue supplier again. And here we ask for the first queue at this stage, which is runtime, and again, 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 and so forth and so on. And in general, for every substream, we will produce a queue in some circumstances. And this is the worst case because, of course, Reactor has some optimizations, but in general, the worst case that we can have in runtime is n queues for n elements from the upstream. So for example, if we have 1,000 of elements, approximately we will create 1,000 of queues, which is a lot. And as you can see here, we use some GC tools queues, which is designed for handling data in multi-threading environment, which means that we will have much more overhead in terms of volatile invocation and so forth and so on. So basically, you should remember when you start using flat maps, when you start using something similar like publish on, you will have to deal with overhead by creation some additional queues during the runtime, because in order to handle data from substreams, in that case, you have to provide a queue and then drain those data from all available queues. All right. So what about publish on? So let me show you that with publish on, we basically have the similar situation. We have the overhead with an additional queue, because in order to send an element onto another worker, for example, in that case, we have to somehow enqueue that element. So we have to somehow put this element into shared memory and give an access to another thread. And in order to do that, we have to use a queue again. And in that case, publish on have something similar under the hood. So at the very beginning, when we start, where we are building our pipeline, we create the request for a queue here. Yeah, here we request for some queue supplier. And basically, for every publish on operator, will be produced another queue. So let me run this plain example again, and let me show you that here we have a request for a queue again. So here we go. And yeah, yes, yeah. Everything is correct, but the queue is a little bit different. So here we have to put a breakpoint here. And if we are going to run this application, we will see, no, why? Maybe here, yeah. Yep. Here we are going to run it again. And here we go. You just saw that we requested for another queue, so we produced another queue to our GC, and which is supposed to handle data between upstream and downstream, but on the different thread. So basically, here we have another queue produced to our runtime, which is another overhead that we can have in our application, and we should remember about such an overhead. All right. The same situation we have for concate map, and the same situation we have for publish. So if you're going to, for example, to look at Flux concate map, we will see the same queue supplier, which means that at runtime, concate map will produce another queue, which means one more or a few more objects for garbage collector. Even so, the GC tools is really optimized. All right. So we just covered some overhead that we can have by produced objects in terms of wrappers of reactive pipelines. We just covered a few points related to method invocation and overheads that we can have by having this chain of responsibility and invocation of this on subscriber and next. And we just ended up with some operators and can impact your performance a lot by producing a lot of additional queues designed for multi-threading. Now we are going to take a look at how we can tune all those overhead. Can we tune it at all, or we can't do that? And what we can do in terms of our performance, in terms of improvements in our performance without changing any line of the code. And first of all, one of the things we can do for our reactive streams is trying to improve inlining during the runtime. And one of the options to, of course, improve the performance is by using, for example, some more powerful JIT compilers like Graal, which means better inlining, which offers better inlining, which offers better escape analysis, which possibly means reducing the number of created objects or reducing the number of wrappers or something like that. So as you have seen, all reactive pipeline is just a wrapper around some small business logic. So could Graal escape that or not? Maybe we should ask Oleg about that later. And also, one of the most excited options and most excited success story about Graal is the story from Twitter, which tells us that we can improve a lot and we can speed up the Scala code, which means that Scala code is basically a functional code, basically functional pipelines, and it could be something similar to what we have in reactive pipelines. So possibly Graal can improve that. So let's take a look. I'm not going to run benchmarks. I'm not going to run everything at live. I'm just going to show you the results that I got during the measurement. Graal based Graal based application versus just Oracle OpenJDK based application. And here is the result. As you can see, the first line, or yeah, the first results is the results of running just plain stream, the same, almost the same application, but using OpenJDK 12. Here at the bottom, we have the same application, absolutely identical code base, but executed using Graal Community Edition. So in order to, so Community Edition is what you can do at the current moment, what you can do just right now by running, by providing a few additional options to your runtime. And all you have to do in your application, you have to, let me quickly show what you can do for your application. And yeah, whether I have or not. Do I have those options? No, I don't have those options, but basically you can provide a few options to your runtime, like unlock additional experimental stuff and providing some additional VM option to your application, like using some uh, additional compiler in your application, which is available out of the box in OpenJDK 12, 11, and 9, of course. And you can have this performance improvement during your runtime of your short-lived streams, which is about maybe, which is, as you can see, it improves the performance, has improved about maybe 6%. And you can have much more improvements for your long live streams, which is about 7 or 8% just for free, just by using Community Edition version of Graal. And what is the most excited, of course, if you have some additional fundings, you can use Enterprise Edition of Graal, which shows much better performance improvements at runtime for short-lived streams as well as for long-lived streams. And here, as you can see, we can have about maybe 2 times better performance comparing to the previous version and comparing to Community Edition, just by using an enterprise version of Graal, which has a better escape analysis and better and better and better inlining. Maybe Oleh Shalaev can comment something on how we can get and why we can have all of those improvements. Oleh, are you with me?
Yes, absolutely. I'm here, and I can comment quickly, fix the screen, your thing. The GraalVM project is the source of the Graal compiler, right? This is where the Graal compiler is developed. The OpenJDK uh, team, people developing OpenJDK, sometimes copy the Graal compiler, the open source version, into the OpenJDK forest, and then when they build OpenJDK, the Graal compiler is there, right? So the easiest way to try the Graal compiler, the community edition, is perhaps to provide a couple of command line options, as I mentioned. Those are the double X unlock experimental VM options and use JVM CI compiler, right? And you will get the Graal CE. The Graal EE, the GraalVM Enterprise Edition, is a proprietary product which you can currently download from the Portal Technology Network. It comes with performance improvements and mostly with more powerful version of the Graal compiler. The most notable optimizations, which are more powerful there, are the inlining algorithms and the polymorphic inlining, which I think plays quite a bit of role on the reactive code, because when you showed those method call chains, right, you went all the time through the same signature, like request, 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 but you actually request different things from different implementation classes.
or on next when you do subscriptions, right? The GraalVM Enterprise Edition compiler can handle those cases much better. But in general, uh, escape analysis, what you mentioned, is excellent in both editions, and both editions can provide you performance improvements for various workloads. Uh, and well, the enterprise edition will be faster than the community edition, so you can opt in using that if you want. But if you
Right.
don't want and you want to stick to the open source, you can measure and you can verify the impact, and you can use the open source that's freely and nice.
Right. So in any case, using the Graal JIT, you can, in some cases, and I would like to pay your attention that in some cases, for example, when you have a huge number of reactive streams within your application, when you have a long chain of pipes or operators within your data processing pipeline, you can have a really huge win by using Graal VM and by using Graal JIT optimization, of course, which happens at runtime. However, as we will see a little bit later, it's a little bit controversial, but I will be talking a bit about that a little bit later. So for now, in general, to summarize, we can have a huge performance improvement just by using, for example, a CE version of Graal. We can win around from 6% to 10%, which is in case of a really huge number of servers, and in case of really huge infrastructure, you can save a lot of funding, and you can save a lot of spends on your infrastructure by just using Graal in your application. Of course. All right. So let's talk a little bit on another optimizations that we can do for our reactive streams. And one of the options that we can tune without changing any line of code is, of course, choosing the GC. So in general, every object that usually goes through reactive pipeline is immutable object. If you don't have immutable object, you should think twice about that, because a lot of you can have a lot of pain by using mutable objects, so you have to probably move to immutable one. And in general, when we are talking about immutable object, and especially about those objects within the stream, we are talking about short-lived objects. And these short-lived objects, GC works very well because all they are occurs in the young generation. And now we have to think which GC works well with short-lived objects and works well with young generation. I'm not going to show you again all these benchmarks. I'm going to show you just a benchmark that I found on the Twitter from David Cornock. David Cornock is the author of one of the authors of RxJava and Reactor 3, and he did some measurements. I did almost similar, but in general, he had much better comparison and table of comparison. And in general, if you're looking for good throughput, you probably should use parallel GC, because parallel GC uses the less number of threads, and in that way allocate less or use less threads for memory and for garbage collecting. However, from my experience and from my experience of building high-performance application in production, in live, and one of the GCs that we are using within our company for running our RSocket infrastructure, here we are using G1 GC, which is also an excellent garbage collector, which is tuned for low latency, and for reactive streams, it shows a really good performance as well, and a really good throughput along with a really good latency. So we are going to play with GC a little bit later, and now we just have to pay attention to those numbers and remember which GC is a little bit better for reactive streams. And finally, the final stage, which I'm going to cover, is some tuning of the operators that I mentioned a few slides ago. And one of the options that we can tune within reactive streams is tuning the size of the queue, because as you can remember, we have a few operators like flat map, like concate map, like publish on, which relies on some queue. And in many cases, we just write a flat map with no additional parameters, just a lambda that converts an element to another stream. And that's the most common what we can do here, and we are doing here, and we do that in most cases. And sometimes we forget about additional options and additional parameters that can impact a lot of your that can impact your performance a lot. However, it's if you forgot to change these additional parameters, if you didn't pay attention to those additional parameters and overloads of, for example, flat map or publish on, you can always tune those parameters in your application by providing additional arguments like reactor buffer size for X small queues and for small queues. And if we're going back to our small demo applications, and if we are going to in order to show you how changing or how tuning of those applications or those parameters can impact your performance, I'm going to tune a little bit of those parameters for this really plain stream. In order to make this more realistic, I'm going to do some warm-up and I'm going to measure some time of execution of this stream. So basically, let me remind you what is going on here. Basically, we create a stream of 1,000 elements, and then we create another 1,000 of substream elements. Since we have some options and some additional overloads for flat map, like prefetch size and concurrency, which means that concurrency is how many substreams we can have at a time within our flat map, or in other words, how many streams can be merged at the same time within one flat map. And prefetch, which means how many elements I would like to request at the first for our internal substream. So it means how many elements I would like to request at first for in our internal stream. And those elements can impact your performance a lot. So let me just show you the average time that this execution takes. So basically, I do some warm-up, so my runtime should be happy with what is going on. And if I'm going to rerun this application, I will basically have the same output. So around 4 seconds. So everything that you can see is in miles. So you have to split that on 1,000 and have 4 seconds. Now, if I'm going to just change the default parameters for my application to, for example, this one. For example, I want to use the smallest queue. I want to set the queue size for the smallest queue for 1,000, for example, elements, and for small 2,000 elements, and the same configuration as you can remember. Absolutely depends on what is going on in flat map. So for default parameters, for no, let's name it no arguments except mapper overload. In that case, the default concurrency and default prefetch size will be derived from small buffer size, which is here, and which could be configured by providing that property. And the prefetch size could be configured by this property, which we can set up in this way. And just by tuning those two options, we can increase our performance maybe in 2 times. Yeah, it's around 1 second and 600 miles here, which is almost 2 times better or 3 times better than previous number, which is good. So basically, we can just simply tune those 2 parameters in order to improve our performance in our application as well. However, you should remember that by tuning those parameters, you have another impact. You have an impact on the memory, because every queue allocation means allocation of the, in the simplest case, allocation of array under the hood, which means that your streams will have much more, will use much more memory than before. So you have to remember about that as well. And the same could be done for publish on and for publish operator and for concate map, because all of them relies on this default. For example, here we use the same small buffer size per default, which means that here we have some prefetch size higher than before. And in that case, it potentially can improve the performance by requesting more elements from asynchronous source. And in that case, we can produce and increase performance as well. And the same applies for concate map and for publish. So when you're going to tune your application, you have to take into account those properties, and you have to play with those properties as well. All right. Now let's take a look at the real application, and now let's try to apply all of those tuning, all of those GVM changes, all of those additional parameters to our real application, and see whether it improves performance or not. So here, let me shortly explain the application that I have here. So here is the image of the application that we are going to work with. So here I have some cluster of services, and here I have a plain Marvel application that allows me to run a tournament between Marvel heroes and choose which Marvel hero is the best one. So I hope this guy will be working. Let me just rerun it. Come on. As usual, it don't want to work. So let me double check whether it's running or not. Just a second, and I will be showing you. Yeah, as usual, I have here some weird issues. Yeah, let me just restore those guys, and let me just restart the broker application in order to ensure that everything is in a good condition. Yeah, so in general, as you have seen, we have at least 4 elements and 4 parts of our system. We have broker, which is our socket broker. We have an record server, which can communicate with database. In this case, we are using a little bit simpler implementation of record service, which just consumes and supplies data to the requester from the memory. And here we have a client. We have a tournament server, which has some business logic in there. So let me quickly go through the pipelines that we have. So in general, here we use some Reactor stuff. We use publish on operator. We use flat map. Here we use subscribe on in order to run our code on the different thread. we use some buffer, we use some additional transformation, and so forth and so on. And since we use here RSocket, which is reactive streams over the network, so RSocket is basically the same reactive streams as we have in Java, but through the network. So it does everything to encode your request and elements to the frame and then decode it on the other side or on the other service, and in that way preserve bug pressure, and it's built on top of and it's built for performance, so it uses only one connection and so forth and so on. And in general, this is the same reactive streams but through the network. That's all you have to know about RSocket for now. Within RSocket, we have another set of course, we have another set of reactive pipelines. So let me quickly go, come on. Another set of reactive pipelines. RSocket on. For some reason, it just hanging. So RSocket, come on, buddy. Yeah, RSocket client. And within RSocket client, we have another set of reactive pipelines. Here, as you can see, we have another set of pipelines here, and so forth and so on. So RSocket is built on top of Project Reactor. It uses a lot of reactive operators under the hood. And I guess this is a good example of reactive streams under the hood as well as within our business logic. And here is a good source for optimization without changing any line of code, because first of all, RSocket is a black box for us. We can't just change it. We just can use it, and that's it. Another black box for us is our broker service, which is an implementation of message broker on top of RSocket. This is a solution that we are building at the current moment, and it relies on RSocket and it relies on reactive programming as well. But this is a black box. This is our proprietary solution, and once you decide to use it, you can just download a Docker image and you can just tune it without in terms of changing the code. So the only thing you can do, you can just change GVM, or you can change Java, or you can provide some additional VM options to our broker, and that's it. That's basically what you can do with this application. So this is another good source of tuning as a demo tuning. And now let me double check whether everything is running. Yeah, let me run it again and hope that this time I will have everything working. And we will be able to play a little bit into. Yeah, we can. Great. So here we just got a question: which hero is better? So we have to choose one. And by doing that, we will send over the WebSocket. So here I'm using only one WebSocket between browser. So there is an implementation of RSocket for GVM, and the same there is implementation for browser. So you can build end-to-end pipeline of reactive streams even through the browser. And here we use only one WebSocket connection in order to send binary messages like request one, request an elements, on next, on subscribe, and so forth and so on. And we can play to this game in order to choose the best. Yeah, here we have some little bugs, but it's fine. It just works, which is great. So now what we are going to do, we are not going to make a load from the browser, but here I have, along with the browser implementation of the Runtime server, I have plain implementation of the Runtime servers as a random, as application that choose almost randomly the best hero by comparing by doing comparison between records, list, and so forth and so on, and story count for every Marvel hero. So we have an implementation of the same Rankin service as an application. And let me just kill my node application here in order to stop using it, using the port. And now I'm going to just run this application here. And on the other hand, I have a client that pretend to make some load. Of course, this is just a naive load client. In the real production, you have to provide much more clients in order to make load on your application. But just for demo purpose, I'm going to use this plain client. I'm going to send some infinitive number of requests by applying retry backoff logic with repeat. So if in case we get some error, I'm going to retry the stream and that's it. So basically, we are going to listening to new data. We are going to send in requests to another services, as explained in this document. So I'm just going I will be making some load through from the client to broker, and broker will redirect the request to tournament, and tournament will send some requests to record service through the broker, and then from the after that stage, tournament server will be sending some ranking requests to ranking server, and after all of this processing, it will send a request back. So it will take a little bit of time, and we will be able to measure this latency, and we will be able how many requests and how many ranking per second can do our plain system. So let me just run this application and start observing what is going on. Let me double check which GVM we use at the moment. So here we are using GDK Open GDK 12. We don't have any additional options. We just have a minimal set of configurations at now. So just that we at the moment we use G1 GC everywhere. So we are going to change this option for every service that we have here in our cluster. And by doing that, we're going to understand how all of those options can improve our performance in real reactive application. So no more words. Let me just run this up, and that's it. So here we go. Our application started. It sends some load. It sends some traffic. And in a second, we will see the performance. So at the moment, the average latency, mean latency on my computer is about 5,000 of microseconds. So it means that the latency is about 5 miles. And total number of requests that I produced is about 500. So something went wrong. Let me just restart all these guys again, because it looks a little bit unstable for now. Yeah, we're going to just restart it after the browser, because browser could cause some issues. And now we're going to restart our app again and see what will happen. So it just runs, and we will wait a little bit in order to understand what is the performance. So here we have average or mean latency about 2 milliseconds. And on average, we can process around 50,000 of requests per second, which is good. So this is a stable. It looks like stable. So now we see that we have 2 milliseconds latency and for almost 5,000 of requests per RPS. So now let's try to tune something in our system, and let's start with just trying to run everything on Graal. And let me start doing that from the broker. Let me just use here a Graal, which is enterprise edition of Graal, in order to understand whether we can improve performance by using Graal here. So let me do that. And let me basically restart this up and stop all these guys in order to prevent them sending some incorrect data. So here we go. We're starting our server, broker server. And as you can see here, we are using GraalVM, the latest GraalVM Enterprise Edition of GraalVM. So everything should be fine. And currently it should be running on top of GraalVM. Yeah, here we go. Now let me try to restart my app. Of course, you should remember that Graal can take some time for warming up the system, for analyzing what is going on under the hood on the bytecode level. So we will give some time for warming up our application, and then we will see what is the throughput we can get with Graal just by changing it on the broker side. So for now, we have latency around 3 milliseconds and around 35,000 of throughputs. So here we have a little bit better, 42, and latency around 3 milliseconds. So yeah, it's just running. So let's wait a little bit. Again, something went wrong. Yeah, weird error. I don't know why it happens. So let me just restart those guys. Let me just restart those guys and rerun this test again in order to make sure we have the correct results of performance on Graal. So a few seconds in order to get the first measurement. Yeah, here we go. Another few seconds in order to make sure it. Okay, again. What's wrong with you, buddy?
This is a very important moment where you can say whether you've seen those errors before switching to GraalVM. Because currently it doesn't look very stable, which is
I don't think this is related to GraalVM because I were able to test to run this test and run those measurements using Graal. Yeah, here we go. Now we have a little bit better mean latency, and yeah, here we go. It works. Great, so it works. So let's wait a little bit for another few measurements. And as you can see, with Graal Enterprise Edition, we can have really good improvements in performance. Which is really interesting is that before I had a little bit different measurements because I got some decrease in performance using Graal, and this is really interesting because as you might know, under the hood and RSocket and the broker uses Netty, and as someone and some of you can know about Netty tuning, the Netty is really uh, well tuned for a C2 compiler, and that's why your application that relies on a pure Netty can perform a little bit less good than with normal OpenGDK JIT or something like that. Maybe Oleh can add something on to my words about Netty optimizations.
well, not really sure. You have to measure, like everything with performance. You have to measure. You have to measure your code and your loads and you and typically we run a lot of benchmarks. We see great results for the GraalVM Enterprise Edition. We see results comparable to the compiler on the GraalVM Edition. The method to make the best timing to be fastest in the Community Edition, and with the Enterprise Edition just providing even more performance boost. But you always measure and always know that if the code is written in a way to be really fast on C2, it's really hard to beat it, right? If something was specifically written to inline really well on C2, it would be hard to be better.
Yeah, right. So that's basically what is going on inside our broker. And actually, within our broker, we were doing everything to run it really fast with Netty, and that's why optimization, Graal optimization on the broker side could be a little bit unfortunate. Thus, we're just going to switch back to JDK 12, and we're going to try Graal on the application that has some reactive code and that relies on reactive programming a lot. And one of those applications is actually a tournament application which uses RSocket, which is written using Reactor and reactive programming, and we have a lot of business logic written in reactive style. So here we can have some improvements. So let's just run our applications. Let's just run them all using Graal and see whether we can have performance improvements here. Let's just try to do that. Of course, as Oleg said, we have to run everything on real environment. You don't have to repeat the same test on your laptop because it's super incorrect. You have to have some additional server for measurements. And only using the correct servers, the correct bare metal servers or cloud servers, you will be able to get the really correct performance results using different VMs. So let's run it again, and let's see whether we will have better performance again or not. And on average, we should have better performance because here we have a lot of reactive programming. We have a lot of, now we have much better throughput and a little bit lower or almost similar latency. But if we will wait a little bit, once we have Graal collected enough data, once it warmed up enough, we will get really good performance. And yeah, in general, it's better than with just plain JDK because currently we have a little bit more. We have 52,000, almost 53,000 RPS per second, which is maybe 3,000 or 4,000 better than for JDK 12, which is a good result. All right, so let's try to tune another options in our environment. For example, let's experiment with some GCs. Let's try to change some GC options, for example, to parallel GC. Currently, we are using GC1. So let's use, for example, parallel GC. I hope I didn't make a mistake here. Yeah, it looks like correct. And let's see how it impacts our performance in this case. So let's do that for all of the applications. Let's do it here as well. Yeah, here we go. And let's do the same for our broker, which is running here. And here I'm going to use parallel GC now. Great, so let me just rerun it again. And let me make sure I'm using the GC, see here. Yeah, I'm using parallel GC right now here. And let me do the same for those guys. Let me just run them with parallel GC. Now we are going to see whether it gives better latency, better performance or not. So you will be able to play on your real application here. And now I'm going to run the client in order to observe the results. So what do we have here? Just a second to collect the results. And here we have a little bit of decrease in latency, I mean, increase in latency. Previously, we had latency around 2 miles. Now we have it a little bit higher. And now we have a little bit lower performance, or not. Let's just wait a little bit because everything is running on Graal. So we have to warm up a little bit. All right, so now we are seeing a little bit better performance with parallel GC. So parallel GC can improve your performance as well, or cannot. In many cases, it depends on the number of clients that is sending data, but you can see the results, which is a little bit better than before, than with GEC1, with garbage collector G1, which is good. So you can try such improvement in real environment as well. All right, now let's try to play with the final properties which I mentioned during my presentation, and those properties is buffer size. So at the moment, I'm using a really small buffer size, and the point is that in Reactor environment, in Spring, which relies on Reactor Netty, those properties are really important because Reactor Netty relies on those properties, and those properties means how many elements Reactor Netty will prefetch at once in order to send data to the network. So Reactor Netty also implemented in the reactive way, but in that case, there is a back pressure just between the network and between your producer. And in order to not overwhelm the network or not overwhelm the channel, it provides some manual flow control, and it uses the same mechanism as in publish on in order to send data to the network. So by changing those properties, we also can improve performance of our application a little bit. So for example, if we are going to set those properties to, for example, 512 and small buffer size, for example, to 2038, we will be able, or we won't be able to see some improvements. Because in many cases, it depends on the speed of the provider, on the many cases, on the network latency, and so forth and so on. So again, in real production, you have to play around with those properties in order to find the golden circle for your application. It's the golden configuration for your application. And now let me set the same for broker in order to make sure every piece of services uses the same buffer size. Now, yeah, it's running. That's great. Now let me just rerun those guys. In order to see whether we have good performance or not. So yeah, here we go. Here we are running our client again. And in a few seconds, we will see the performance measurement again. So currently we are running on Graal. If I'm correct, yeah, we are running on the Graal. we are using parallel GC under the hood. And as you can see, we got some improvements in latency again by changing the buffer size, because in many cases, the prefetch size and the size of the request batch can improve and can impact our performance in a good sense. And as you can see, by just changing the buffer size, which means changing the prefetch size, we improved our throughput and our latency a little bit, which is great for us. Yeah, that's good. So all of these changes which I mentioned can improve your performance, and you have to play around with those with all of those properties. You have to definitely try GraalVM Enterprise Edition in order to understand how it runs and how it improves your application. You definitely have to try in case you can't use Enterprise Edition and you can't have enough money to have proprietary edition of GraalVM. You are always able to try. You are always able to try CA or community edition of Graal, which is built in OpenJDK 9, 11, and 12, as far as I remember. And you will be able to get some improvements for free. Also, once you are relying on reactive application, once you are using Reactor, once you are using Reactive Spring, you have this application in production, you don't have an access to changing changing the code. You don't have time to, or I don't know. There is some reasons when you can't change the code base, and the only option is just to play around with VM options. You have to remember about such an options like queue size, which absolutely reflect on the performance of the application and reflect on how many elements we are going to prefetch at once, which can improve your performance as well. However, you have to remember about the other downside of such changes, because the more queue size we provide, the more elements we have to keep in the memory. And in case of not enough memory, or in case of really small applications, such changes can just cause the crash of your application. It can cause out of memory or another incident during the real production. So you have to really carefully change those properties, taking into account all possible impacts that they can provide. Finally, you have to remember that GC is also important part of the application, and by choosing the right GC, by understanding what is going on inside your flow, by understanding how many elements you're producing during the runtime, by understanding how many threads, for example, executing at the time in your application, you will be able to produce and improve the performance as well. Because as you might remember, reactive streams is about short-lived immutable objects in most cases. So all objects is short-lived, and for example, G1 or parallel GC can handle all of those objects really fast without huge impact on average or general application performance. All right, so I guess this is basically it. Any question is welcome. I'm going to share all the code, all the samples that I have shown during the presentation with you in the chat, in the Slack channel. And now everyone who is alive at the moment are welcome to ask any question. And thank you for your attention.
Thank you, Oleg. That was absolutely excellent. That was brilliant. I learned a ton. myself. It was very nice to listen to this and to follow you on this journey. Uh, Unfortunately, I think we run a little bit over time.
Yeah, I saw
There were
that.
a couple of questions in the live chat in the Slack channel. I would try to relate them to you, but I don't want to take any more of your time right now in this video. So I would try to communicate to you, and I would invite you to the Slack so you can answer them. Uh,
Yeah, sure
but
thing.
all in all, like, thank you very much. It was a brilliant session. Thank you for everyone watching. We gonna The video will be available on YouTube, and we'll see you next time on the virtual rec session. So thank you, Oleg. Thank you, everyone who's watching us. Follow Oleg. He goes at Twitter on Twitter by at Oleg Dokuka. Follow him. Ask him any questions. If you have any performance problems with your reactive applications, you know the expert to talk to. And all the materials will be online, right?
Yeah, yeah. Thank you, Oleg, for invitation. It's a great experience to talking to my computer. It's funny because I used to mostly talking to real people face to face. So thank you for great experience. This is the first, actually, this is the first version of my reactive presentation. This is the first draft. So if you have any question, they are welcome. I will be presenting another version, which is about some more code full tuning of reactive streams. So yeah, I will ping you once I will make it. And yeah, thank you. Thank you a lot. And you're welcome to ping me.
Thank you very much once again. See you next time.
See you.
Bye.
Bye.